So our third pass through the what is a fluid content doesn't actually add any new ideas. It's just going to apply the ideas that we've seen to more complicated situations. The first of those is more complicated viscosity problems. And really all this comes down to is taking those differential elements and integrating them, but we're going to encounter more complex geometry. So let's get started. This really is just an example. Let's see here. How do I get rid of that? Go away. There we go. Okay, so an expert level viscosity problem. Here we have a pivot bearing, okay, which is a thing that comes to a point and it goes down in this little V-shaped groove, which would, all of this is round. And it spins and it floats on this little oil film, and that keeps it from wiggling around. And what we want to know is what's the torque required to turn this. We're told that we can assume it's a linear velocity profile, but the thing that's strange is that that linear velocity profile is on an angle here where this outer wall is stationary and this inner wall is spinning, but it's on some angle. Remember that we defined the shear as mu du dy. We could then take a differential force by multiplying that shear by a differential area, and we can find a differential torque by multiplying the differential force by a radius that it acts on, r tau dA. And so that's what we're going to work on here, because we're looking for the torque to drive this thing. Right out of the gate, the thing that's weird is that because r changes, we're going to end up with a changing max velocity, which changes the velocity gradient that affects the shear stress. Okay, so where we're going to start is by defining dA. Define dA. And this really is the crux of the problem. So I just want to zoom in on this region a little bit, make it easier for us to visualize here. So here's the center line of our spindle, and the wall of the spindle comes up like so at an angle. And then offset from that some distance is the outer wall. This wall is, of course, stationary. This inner wall is rotating, and we defined this as an angle called phi. And this gap here was called b. That's the thickness of the gap, b. And so this thing rotates. The thing that's strange is our differential area is right there. This is our differential area. And so how are we going to handle that? Well, part of it we're comfortable with already. That's the part going into the page. That's the theta part. And so we have a dA that looks like r d theta. That's the arc length going into the page of our differential element. And then what we're going to do is define a new coordinate right here, and this is the trick, called dl. And so our differential area is r d theta dl, which gives us this little box, and you could integrate that to get what we want. The question is, what is dl? Well, that's going to come from playing some triangle games here. So let me just draw this a little bit bigger. Okay, we have a thing that looks like this, where this distance here is dr. It's coming out this way. And then this distance here we called dl. And of course we have the angle here, which is phi. And so this triangle says that the sine of phi is equal to dr over dl, right? Opposite over hypotenuse. And so we can rearrange this and find that dl then is equal to the dr over the sine of phi. So if I sub that in, I get my differential area in terms of my fundamental coordinate system, r d theta, that's this part, and then we're going to replace the dl with a dr, but we have to divide by the sine phi. Okay, so there's our differential area. That's really the tricky part. Okay, let's keep going here. The next thing we want to think about is the torque, right? We said that a differential torque is equal to R times the differential force, or R times the shear times the differential area. And at this point, what do we know? Well, we've got our coordinate system R and we've got our differential area. We just came up with that. And so the thing we need to work out still is our torque, or our shear stress, tau. And tau, remember, is equal to mu du dy, and we're going to evaluate that at the wall. So let's come back up here for just a second and define a coordinate system for the sake of this. Let's call y this one. Oops. Y goes this way out from the wall, and we have our height b. And so we can then write y equals 0 as the place that we want our shear stress to be. And we were told this is a linear profile, so u as a function of y is still equal to the velocity at the wall here, which we could call u of y equals 0 divided by b. And of course I've run out of space. Let me just move this over. Times y. That's the linear profile that we've done a bunch of times. And we know that the velocity at the wall here can be found like we did in other rotating problems as r omega. And so we can write that u of y is equal to r omega over b times y. If we sub that in, we get that the shear stress is equal to mu d by dy of r omega over b times y. And of course we'd evaluate that at y equals 0, but because it's linear, the y is going to go away, and this really doesn't have much meaning to us other than, let's take the derivative. So tau here is equal to mu, take the derivative of this with respect to y, and that just leaves the r omega over b, and the y drops out. And draw ourselves a nice little dash box around that. And that gives us the last of the ingredients that we need to evaluate this thing. So believe it or not, we're only a couple lines away from solving it. One more time, what we did was first we found our differential area. That was tricky because it's on an angle, but we worked that out here. And then we found our shear stress for a linear profile in that gap in terms of r omega. And so now we're just going to sub everything into this differential torque and integrate as appropriate. So let's get there. Okay, there's the top of that. And so we're going to have a differential torque, which will be equal to R. Then we had the shear stress, which was mu r omega over b. And we want to multiply that by the differential area, which we came up with as r d theta dr divided by sine phi, which is the angle of the point there. And just remember that we can always switch back and forth, right? The radius is just equal to diameter over 2. Don't think we need to beat that one into the ground too much here, but we do need to integrate this thing. And so on the left-hand side, we integrate our differential torque, and on the right-hand side, we're going to have a double integral because we've got a dr and a d theta. I'm just going to collect the like terms here so we can make it mu omega over b sine phi. We've got 1, 2, 3 r's, so that's an r cubed d theta dr. And the limits on this are going to go, since that thing came to a point, from 0 to r. That's going out to the radius at the end of that tapered pointed area. And we're going to do a full circle because we're going the whole way around our object, and so theta goes from 0 to 2 pi. And so if we evaluate this integral, first we do it for theta here. Nothing is a function of theta, and so we're left with the torque being equal to just a 2 pi. That's the integral of theta evaluated. Mu omega over b sine phi. And then that has to get integrated from 0 to r of r cubed dr. And the integral of r cubed is just r to the 4 over 4, right? Because we're going from 0 to r. And if you sub that in, simplify a little bit, we get that the torque is equal to pi times mu times omega over 2b sine phi r to the 4th. So although the math looked a little strange, all we did was come up with a more complicated version of the differential area and then integrate it.